Hi guys, I'm going to demonstrate problem 6.P.90 in Matter and Interactions Volume 1. Here we are standing on an asteroid which has a certain mass and also a certain radius, and we want to throw a rock so that it never comes back to the asteroid and actually has some leftover speed when it's very far away. So this is clearly not something you can do on Earth, and we'll see why in the equation you can't do this on Earth. But on this particular asteroid, it is possible to throw a rock out to infinity. Alright, so here we are. Here's the asteroid. Here's you throwing the rock, and the rock ends up far away. Well, as usual, in these types of problems, we can consider the energy principle, and energy is conserved here because the rock doesn't lose any energy after it, or gain any energy after it leaves your hand. So the total energy is constant. All right, total energy consists of kinetic and potential. And at this point, it's always a good idea to consider which of these terms might be zero, because that makes things a little bit easier. Kinetic final's definitely not zero, because it says it's supposed to have 3 meters per second in the final state. Right? U final, well, it's at infinity, so U final is zero. So we don't need to consider that. It does have an initial kinetic, because it leaves your hand at some speed, so that's not zero. And UI is also not zero because it's close to the asteroid in the initial case. And we just have to solve this. Notice that each term has the mass of the rock in it, so we can cancel that. We can multiply by 2. Then we can bring up our calculator, and then there we go. We get 16.6 meters per second. I guess that's reasonable. Maybe we could throw something that fast. Notice there's really nothing in this equation that assumes we're talking about an asteroid. We could just as easily be talking about the Earth if we replaced this mass by the Earth mass and this radius by the Earth radius. So let's do that for fun and just see what happens. So if we put that in, we get that we have to throw the ball at a cool almost 12,000 meters per second. Well, that's why you won't be throwing a rock out into space anytime soon. And basically that's because the Earth is very heavy. That's a large number right there. So that makes it impossible to throw something at escape velocity. But mechanically, maybe you could shoot it out to infinity, or with a rocket booster you could get it out to infinity. So the last thing we need to do is sketch the kinetic energy, potential energy, and the total energy on a graph. Okay. Well, let's start with potential energy. That's usually the easiest one because it's always the same for these type of problems. It's always minus GMM over R. So that's minus 1 over R. It's a hyperbola. It has asymptotes on the vertical and on the horizontal. Total energy. Well, total energy in the final state is still positive because it has this leftover energy associated with the final speed. So it should be some positive number. And whatever the total energy is in the final state, it's always going to be the same because energy is conserved. And then we could draw the kinetic energy. We know that in the final state, the kinetic energy is the total energy because there's no potential. So we could start drawing the kinetic here. And basically, whatever the potential does, the kinetic needs to do the opposite of that. So as the potential decreases going towards the asteroid, the kinetic should increase. We could easily consider this problem for the case that it ends up traveling at 0 meters per second, so that it just barely escapes instead of has some leftover energy after escaping. And all we would have to do to show that would be to take our total energy and move it to 0, because if it's slow and far away, that means 0 total energy. So that would be the total energy in the 0 far away case. and you just have to bring the kinetic energy down so it asymptotes to that total energy. There. So that's the case where it just barely escapes. And if we wanted to solve for what velocity at which that occurs, we could simply go back to our formula, and Vf would be 0 in that case. So we can really use the same formula, just with a different Vf. Finally, we might want to know what happens if you throw that rock up, like on Earth, and it doesn't escape, but it comes down back to you. Then what would the graph look like? Alright, well, as usual, we can just take the total energy and move it down somewhere. And potential energy is always the same, so it still looks like that. But the thing is that, in this case, the particle can never, or the rock can never go past this point here. So it can never go to the right of this line, because at this point, the total energy is all potential, and the potential can increase no more. And then we can go about drawing kinetic as usual. Well, it's going to stop at that point. That represents when you throw that rock up, that rock is going to stop eventually. So that's occurring at this particular radius. Right. So those are the three cases of interest that we might want to talk about. Notice that we can't use this formula if we wanted to know, say, at what height the rock would stop, because we've already assumed that U final is 0, which would not be the case if the rock did not escape to infinity. So if we want to know when the rock stops and comes back, then we need to rethink this formula. U final is not 0. There is one thing that's 0, though. If it stops, let's say that's the final state, that term would end up being 0. So then we would have to write out each of the terms. We could say radius plus whatever height it goes to, where h would be whatever height above the surface of the asteroid we get to. Okay, and again, the mass of the rock cancels out. Given some initial velocity, we could figure out how high it goes. That's pretty much all the problems or the permutations of this problem that I can think of. It's good to understand this one front and back, because really all of the different scenarios here come from starting with the energy equation and then just evaluating the terms.